Okay, recap on protein structure prediction. Again, we will receive the entire data set of all known features that we have, or all the experimental data that we have as the pi. And we have to take some part of the pi out to do cross-validation. So brain training, cross-training and testing. One example for what we use the cross-training for is to decide when to stop training. So in this decision, so this should be light green now, it's no longer decided on the testing set, because the testing set cannot be used to optimize any parameter. So this should be a light green line here, it's not the testing, should be a cross-training set. And then the cross-training set would be used to decide that at this point, that point, or whatever point, one of these two here, you stop the training. Okay? That is one example for what you use the cross-training for. I showed you the simplest device that uses a sparse coding, where we have for 20 amino acids and 21 component input vector, the 20 amino acids plus a spacer, of which 20 are 0, 1 is 1, shown here as a proline. The input to the entire neural network here is on the left-hand side, 13 consecutive residues taken out of the protein, and then it's 13 times 21 input units, and 3 output units for other beta strand or extended and helix. So the device predicts whether or not the central residue here at the proline is in which of these 3 secondary structure states it is. The device, in fact, will, so we will get back to that in a moment, but say my output here, the values, the output value would be 0.5, 0.4, and 0.1. So the other unit is 0.1, the E unit is 0.4, the H unit is 0.5, then this decision is trivial. Right? What is the decision? What is the prediction? So this is example 1. What's the prediction?
H.
Yeah. Start value simply is the highest. The system will make a prediction, it will choose that of the output values to be predicted, whatever is highest. So if the output were to be 0.8, 0.1, 0.1, here example 2, again, the decision is exactly the same for these 2 examples. In both cases, the first unit is the highest. In both cases, this neural network predicts as the proline to be in the state helix, the central one. Okay? In the second example, the prediction is stronger. I will show you what we can use the strength for a little bit later. Now, what I did show you is that you can train this in 2 different ways, in a balanced and a non-balanced way. Do you remember what these are? Everybody remembers it? So, essentially the idea is that the unbalanced way is the way in which these states exist in the database. And that leads to a situation, so this axis shows time. Time is measured as in repetitions of training. So every one of these steps, you present every single sample in the database once. This is the way it's used here, this unit. So if you have 2 million, so this is 2 million training steps, 4 million, 3 times 2, 6, and so forth. And the progress for the 3 secondary structure states, helix, red, other, green, and beta strand, what you saw, if you present fewer beta strands, because there are fewer beta strands in the data set, about 20-something%, the beta strand is trained, is learned the last, takes the longest to be trained, simply because there are so few. That gave the idea that maybe due to the fact that there are so few of those. In fact, when we do use a balanced set, in the balanced set you present each, and it's a sample randomly chosen from each of these 3 classes at the same time, at one time point. And you sort of sum over 3 samples every single time. So in this one here you present 1 example at a time, in this one here you present 3 samples at a time. And these 3 are chosen such that all 3 states are sampled equally. Now this balanced, in the sense it's balanced that all 3 states are sampled equally, but they are unbalanced is the wrong word, but they are not as they occur in the database. Because the database is just like this one, right? And you do see that the performance for all 3 of them is similar here, the training performance, and in fact also the final test performance. The pi here is the correctly predicted residues, And of these correctly predicted residues, there's an equal portion for alpha helix, beta strand, and other. While in this particular case, for the unbalanced training, what you get is that most correctly predicted residues are in the state other, or loop. The second highest is helix, and then comes beta strand. In fact, beta strand in this particular case is predicted, again, slightly better than random, 40%, but not much better, while here it's pretty exactly equally good. Okay? And I said that this is important because it proves that the statement beta strand formation is less local. We have a window of 30 consecutive residues, so beta strands are not seeing the binding partner. That's why beta strands are predicted less accurately, as this one does. This is not true. I use the same window. I changed nothing in terms of the global versus local information. I'm not bringing in any more local information, just throw in more beta strands. And I get this. So this means that the local window, so 13 consecutive residues, or whatever you put into this device, in this particular case, it was 7, happened to have been 17. That's not relevant. What is relevant? That this local window can predict the same, can yield the same performance for beta strand and alpha helix, which means that the signal in this window is identical. Okay? Although it is true that beta strand formation is non-local, but there's as much local information available to predict beta strand as there is for predicting helix. It may be counterintuitive, but this is proven. And in fact, this was never proven before, so you need a machine learning device to really make that point. Later, people sort of reproduced this with other devices, actually, initially with machine learning devices. But anyway. Okay, so then now through this machine learning device, what we could attack is this issue of beta strand, so we're doing much better for beta strand. So there are two other issues. One is the issue of short segments, and we have addressed that. We haven't addressed that, so that issue is still open. Did I give you the solution how you can make the segments longer? Do you remember the problem with the segments? I sort of gathered up this. So this problem is solved, that's why it's green. Here's the story with short segments. Short segments, the problem there is if you, the ho-ho-ho, I present it as the ho-ho-ho problem. So if your device predicts H-O-H-O-H-O, so residue 1, 2, 3, 4, 5, 6, I'm showing the prediction for 6 residues, then we know that this prediction can absolutely not be right. What we do not know is whether this actually is a very long helix, or whether we should switch the O's to H's, or whether we should switch some of the H's to so it could be that the real thing here has more H's here, because we know that helices have to be at least 3 residues long, or 4 residues long. Because I and I plus 4, so 5 residues long. There's a 310 helix, so that has. But anyway, so we know that helices have a minimal length, so it cannot be H-O-H-O-H-O. How can we change that? How can we put that into the system? The reason why the system made these mistakes is because it never learned that helices have to have a minimal length. Because at different time points it picks, I said I'm averaging here over samples in my training dynamics here. So here, when this one comes up here, I said I picked one sample from each of the 3 classes, but still the samples I picked randomly from my entire data set. So I have 2 million residues from 10,000 proteins, for which I know the secondary structure, and they come into one big stack. And then I choose randomly from that big stack. I'm not looking at correlations, so I'm not training on residue I and I plus 1 and I plus 3, so it will never learn that the sample before was a short helix, so I have to make it longer. It will not see this correlation. If I begin to do that, then I actually make other mistakes. Let's not get into that. So I cannot introduce the correlation that helices have to have a minimal length by changing the training dynamics. How could I put that into the system? How could I put the fact that helices have a minimal length, that strands cannot be 2 residues long, or most strands are not 2 residues long, things like that. Even most loops are longer. A loop on average is also 5 residues long. So this is wrong here, the H, O is wrong for the H, but it's also wrong for the O. So much more likely to be something such as this one here. Anyway, how can I put that into my system? Right.
Use another neural network, for example, and put the output of the first one and the second one, and use the linear length.
Why are you saying that? Yes, we could do that. So that is what I assume she just said. So what I showed here is the level network that I showed you before. So where the sequence is input, so 13 consecutive lobs here, 13 times 21 input units, 3 output units, 1, 2, 3. And that's for one residue. Now I move this network further, second residue, third residue. So I'm showing for a window of 3. Now the input to my second level network, the output of my second level is the same HEL, that's HEO. The input is the output from the first level. So I train a neural network to predict secondary structure, and then I take this network, I run it through my plotting, and I put the prediction of the first level into the second level. The reason why the number of input units here is not 3 times 3, but 3 times 4 is
Adding additional information?
yeah, but what specifically? That's true. Do you remember? Yeah. Exactly. So what I predict, the method predicts the secondary structure of the central residue. If the central residue has to be the first residue, then ahead of it, so in this particular case the window is 13 residues long, so there are 6 residues before the central. So if the first residue is in the center of the window, then 6 residues before it are empty, are non-amino acids. So that's what the spacer unit has been used for here. That's why this is actually 21, not 20, right? And this is the same thing now. So if I use the second level, then again I need a spacer. That is, you're right, we could also put different information as an input, but first of all, before we do that, the minimal thing really is 3 plus 1 for every single one. So now in this particular case here, I really have a central of 3, a window that is of 3. In reality, for my system, I will use a longer one. So in fact, I use 21 for my first approach. It's just difficult to draw. So the 3 I drew, but just imagine that we have 21, right? So again, as before, except for the only thing that is different now is the input is the output from the first level, right? Everything else, same number of hidden units, some number of hidden units, same number of output units. And this system produces the first level, produce beta strands of length on average 3, helices of 4. This one here now is the beta strand to 6, and the helix to more than 6, 1, 2, 3, 4, 5, 6, 7. Compared to observed, so this is much more similar to the observed. I haven't shown that? Yes, I have. So you're cheating. Okay, I can live with that. So what I show here, that's why I remember, because I didn't explain it last time, or I briefly explained it. So this is the length of a secondary structure segment, so alpha, helices, beta strand, and other all put into one big pot. Blue is those are the numbers, so histogram. Blue is predicted, red is observed, DSSP. And you see that essentially, except for there are a few short ones here that are not predicted. So this peak here is not predicted, and there's some reason for that. That is boring. But other than that, so this is just a zoom into this region here. But other than that, the blue and the red are similar. So it's not only predicting the average length right, but it also predicts at least the distribution of segments. So this system has learned, clearly has learned the length of secondary structure sector, but nothing else than putting the output from the first level into the second level. It has not used any other information. All it has learned essentially is this distribution, without explicitly being taught. It has not been taught the length of it. So the additional unit that Louis suspected there could have been something such as the overall length of the segment. I could have put that in, or something, but I didn't. And there's a reason. This is the same drawing, but in this particular case here for helix strand and loop, and there's a differential. It's observed minus predicted, where again, you see some differences, but they are remarkably similar. The idea of the second level network was introduced, in fact, by Chang and Sinofsky in '88. Here's the solution that came 5 years later, and the reason why it was sort of reinvented, why I reinvented this, is because when they introduced it, they never looked at the segment. They never looked at length. They used the second level to improve over the first level, and that didn't work. It didn't improve over the first level. So the second level network used as something that sort of refines the prediction. As that, it didn't work. Or it improved, but not in any significant way. So in fact, they claimed it improved, but in my hands it didn't work. But it really did work wonders for the second prediction. Okay, so I will not go into this. Here's a different solution that approaches the problem here. And now, what I showed you before is sort of this 90 degrees around. This is the input now. This is the output. Okay, previously the output was on that side and the input was on that side. So this is the 90 degree rotation. It's a type of method, recurrent network. I should have put the word up here. Sorry, I didn't. The idea comes from Paolo Frasconi, and later was put by Gianluca Polastri and Pierre Baldi into used for this problem of secondary structure prediction, where in fact the output from the first level is sort of fed in. But this is no longer a first level and second level. This is one device, where simply the current predicted output from the network moved on further is put back in as input. And so this recurrent network thereby sort of sees what the flanking prediction of the first step are. Okay? Okay? You essentially this is the ith amino acid, and then you have something from the training step of the amino acid before. And you get the level of those. So you previously, and you can also compute the ones at a zero level, you just have a random prediction, right? And then the system refines how it goes. So this is sort of an immanent way of putting the information that you want to put into the system back into one system. The beauty is now you control it all in one system. The disadvantage is a bit more complicated to train these devices. So now we have a machine learning device, either way. So with the first and second level, with a recurrent network. In both cases, I have a machine learning device that now does better for beta strands and does better for seconds. But the overall performance is still only 60+%. So how can we improve that? And that ultimately gets us to this, what I would refer to as the third generation of secondary structure prediction methods. So the first one used a single amino acid, the second one used windows, and then some bells and whistles, some refinements here through machine learning that I showed you. And the third generation really pushes beyond the 60%. And the way to push beyond the 60% is we need to put more information into my input. How can I do that? So let's get back to this slide that I've been showing a couple of times. And let's just revise the way of showing it. And so what it shows here is number of residues in line, percentage sequence identity for a pair of residues. And I have been saying that if the blue proteins naturally evolved in the blue have similar structures. So if two proteins have over 100 residues aligned, and of these 100 residues, at least 33 are identical, then essentially these two have similar structures. Now that means that you can change 67 not 67%, 67 residues in 100 without changing structure. That's what this slide says. Now I'm telling you, I take a protein that is 100 residues long, I randomly choose 5 residues, or even with my intelligence, it doesn't make a difference, and I will knock out the structure. So I claim that if you do the same thing, I randomly choose 5 residues in a protein. These 5 residues will change the structure. Most likely, I said knock out, most likely you will not sort of get a structure that is a good structure that you can do a crystal for. So you will not create some protein that really folds in a good way. Reproducible the same way. That's good. That's good. So how can these two statements be true at the same time? How can it be true that this implies that proteins, 67 residues are different, and proteins that are 100 residues long have similar structure? Yet I say that if you randomly choose 5, you will change structure. These 67 are neutral with respect to structure. That is what it means that they have similar structure, right? How can these statements be true at the same time?
Maybe those vertically are more potent.
Yeah. So this is the kind of example, if you write this in an examination, and then typically I would say, yeah, there's something true there, I will give you some points, but you're not quite nailing it. So this means you're not getting the top number of points. So your statement is compatible with the correct answer, but it's too vague. And this is also a statement for the examination. Try to really put, if it is about bullet points, so if you try to answer a question with just a few bullet points, you have to really nail it. You have to have the right bullet points. So if something requires 3 words, and you throw 30 at me, and the 3 are in there, at some point I'm going to stop reading. So this is not this example. So Tatjana did not throw 30 at me. But this was a little too vague. Can somebody refine it? Again, the question is, why is it true that if I take 5 amino acids, change 5 amino acids, 5 residues at random, I will change the structure, while in nature you see that 67 and 100 are changed and it's neutral. How can these two statements that are completely opposite of each other be true at the same time?
Because there's a constraint, like an evolutionary constraint. Like the
That's
proteins that change, they don't.
So this is sort of nailing it. This is 100%. Yes, and you see some more important presence, but the real issue is evolution. There's an evolutionary constraint. There's an evolutionary selection. This is 100. That's exactly the answer. So proteins evolve. What we see here are the ones that in fact do not change structure. If they would change structure, most of those we would not see, because they would not function. They would not do the right thing. The organism wouldn't survive in some cases. But certainly that change would not be, or in some cases may be beneficial, but in most cases we will not see it because it will do damage. In most cases what we see are the neutral changes. In some sense you can say what we see are the survivors. Survivors is a little bit misleading term here, but in the terms of the protein world, somehow the survivors are the ones that are so neutral that they can in fact do the same thing despite changes, right? That's some way of defining survivors. In that sense, what you see is the record of all the subset of things that are not changing structure, the record of the least likely changes. The most likely changes change structure will not be visible. Those we don't see because they will not be visible by definition, right? So evolution has enough time to select the extremely unlikely scenario. The extremely unlikely scenario, many neutral changes go on. Neutral changes. 67 is as far as evolution has gone by having tried out many others that didn't work. In order to find these 67, that is now getting to Tatjana's point. In order to find these 67, or the information where these things can be changed, what residue, at what position can I change which amino acid against which other amino acid? That is what contains a lot of information about that particular structure. So Tatiana said that as some residues are more important. Yes. And shown in this multiple alignment here, where you see that 4 places are much more conserved in this family than all the others. These are the most important residues in that family in some sense. So if you now align something else into that family, first you look at those 4 places. But ultimately what this shows is an evolutionary constraint that's underneath it. This is just a fossil record of the evolutionary constraint. And the evolutionary constraint contains information about that structure. Let me show you an example for what type of information. So when you look at the 3D structure here, the first residue that is conserved is this one, and the last is conserved is this one. You see, they happen to be next in 3D. So they are relatively far away in terms of sequence space, but they are very close in terms of structure. I mean, they are neighbors, structure, 3D neighbors, right? The other 2, by the way, happen to be on the other side of the molecule. I'm not going into that. Now, what is important, if you now imagine you take out 5 consecutive residues here, and you look at the profile for these 5 consecutive residues, then in this profile, what you can change here has to do with what is here. The type of residues you can observe here in this family has to do with what this one is, because the 2 are binding. They are coupled. So that means that in this 5 consecutive residues from this position here, in the alignment, I have a glimpse at what happens here, because it evolves as a 3-dimensional object. It doesn't evolve as a structural sequence, it evolves as a 3-dimensional object. That means that whatever is observed in this 5 here is influenced by what is here. Or turn that around. In these 5, I have information about the rest of the protein. Because everything of the protein that, certainly in the first round, everything that is next to this one influences this one, wherever in sequence it comes from. So it means, if you think about it, it's like sort of you take a raindrop, 5 consecutive residues is the little part, and in the raindrop you see the world. You see something that is outside of the raindrop. Right? This analogy is what I like a lot because it really is correct here. You see something, you may not see it explicitly. It's not, in that sense, it's not like the raindrop where you really explicitly have a mirror image. But what you observe here has to do with what is here. From what you observe, you may not quite find out what is here. But at least you have traces of it. And this I have to gloss over. So ultimately, that means now for my secondary structure prediction, rather than taking sequence as input, for instance this sparse coding here, I replace at every single position, this is 13 consecutive residues, instead of the sequence, I use the counts in the alignment. Okay? And then I simply put the probability of the alignment into this new network. Everything else is the same. Output is the same, input unit is the same. It's only that I change the input by the counts. So again, what I showed here is the protein sequence. And then 4 proteins that are aligned to it. So this is a family alignment of 5. And at every single position, so the P is in the center here. In the particular case of the P, I have 5 P's. So in this particular case, I would have the same input as if I had only the P. 100% goes to the proline. But in some other cases here, you see that more than 1 amino acids are possible. Here in this particular case, you have 4 different amino acids that are possible. And at every single position, for every single one of these, you put in simply the probability of the fraction of the observed amino acids. Idea clear? Anything unclear? Any question? This is blown up here, just to show the counts again. And this is the one that I said here, there are 4 different amino acids. Could you do it in any other way? So the idea from these was to use evolutionary information or profiles. Could you do it in a different way? So since they do not have a lot of diversity, that a particular position is completely conserved is trivial. if you have 5 times almost the same protein, then every position is almost conserved. That does not mean that that position is important. It only means that we don't have enough diversity. So I take the idea of Nabil or Nabil?
Nabil.
Nabil, I take the idea of Nabil to essentially imply that what we want is sort of a weighing scheme that uses 2 things. It uses an overall score. So how surprising is it that that particular position is conserved given the overall divergence of that family, right? And this, in fact, is something that is used, often is referred to as a conservation rate, and that helps very much here. The other part of Nabil's idea, I believe I understood to be that the smaller the alignment, the more you want to go sort of back to something that resembles a blossom matrix, that resembles a generic exchange, or computes essentially what's the surprise of that particular conservation, or what's the surprise of that finding that you have, given something that you know for all proteins and what you know for that family. Those are the 2 components that you would sort of use as a weight for the conservation position. That's a great idea, yes. And in fact, that really helps. And that brings us back to something that I was surprised nobody said. You could simply put the psi-glass output directly into the system. Because psi-glass at the end has a matrix that somehow tries to compile a position-specific profile that considers these probabilities. That in fact sort of folds the information you get from the particular example of the alignment that you have and pairwise alignments, and puts that into a probability matrix. In the probability matrix that is not the count probability, but a probability as in how surprising is it to find that conservation that you see. And that in fact is what some methods do. Cypress from David Jones is a prominent example of a method that does that. Very successful. Leave it here. Now, when you run the secondary structure prediction method, that means that now things got a little more complicated. So rather than just applying a machine learning device, now you begin with a sequence, you compare it to the database, you do various levels of alignments, you do a decision of what you can include in the family, you extract it in the alignment, you extract the profile, and you put that into my 2 levels of networks. And my 2 levels of network here, as shown before, except for I also add some global information. Global information, for instance, for the entire protein was the amino acid composition, 20 units. What's the length? And that is done with 4 units, not with 1. And what's my current window that I slide through? How close to the beginning of the protein and how close to the end of the protein? Where, with respect to my protein ends, am I? All of this is additional information. There's a first level, there's a second level. Both of those get this additional global information. And then they predict secondary structure. Now, I said that there's the balance training. The balance training gets a performance of, that is not using profile. So in a much simpler setting, the performance was sort of 62% for unbalanced. So that is much better for the state other. And 60%, so this is a Q3. What fraction of residues is correctly predicted in either of those 3 states? And for balance, for which beta strand is predicted equally accurately as helices, you get 60%. Now, that means you have 2 different solutions, and then you do the second level of that. In the second level, you can also do that. So you do unbalanced first, balanced second. You do unbalanced first, unbalanced second, and blah, blah. So you have 4 possibilities to combine these networks. So you have 4 different solutions. Some of them are better at predicting beta strands. Some of them are better at predicting overall the number of residues correctly. What do you do with these 4? So one option is you decide on 1 and throw 3 away. That's one thing to do. Which one would you choose? You would tend to say the one that is more accurate, of course. In this particular case here, that would be this one. But then I had a case to argue that there is an extreme value in predicting beta strands better. So that would be then the one that has a lower level, 60%, Q3, but does way better for beta strongs. So there's a reason. Maybe if you, well, one way of doing it, you could run this one here and say, and see, are there many beta strand residues in your plotting? If you don't find any, you go back to the other one, or something like that. That's one way in which you could do it. Actually, it would be a clever way. So you put a tree on into the system. But what else could you do? Okay, let's try differently. So you train a neural network, and the neural network has 15 hidden units, and it reaches a certain level of Q3. That is, I'm making up the example. So my neural network is with hidden equals 15 is 62, and you get another one with hidden equals 18 is also 62. Which one do you take?
Maybe 1 over 15 because the other 3 units obviously don't turn.
That's a very fair argument. So the other, so statement number 1 is the 3 additional units obviously didn't count. At least as long as I can tell from a single criterion. Maybe you have to now look at other criteria. But for the single criterion I'm currently looking at, it didn't bring anything, and that means I'm sort of using something without any value. That's a very good argument. The other argument would be that the 18th unit don't bring me anything and they take more CPU time. The third argument could be that the 3 units don't bring me anything, and the danger of some sort of over-optimization is always higher because I have more free parameters that are optimized without really gaining anything, and that is always a little bit sort of sign for being concerned. That is true.